there's cards with the number and the name of the country. And so basically when it's your turn, someone else picks a card for you. They tell you the name of the country and you have to guess what number it is on the map. For what country and what continent?
All
you actually
right.
might be right.
So here we are again, basically the kind of the second half-ish of the semester. We had just finished up chapter 16 before break, and so we're going to be moving into chapter 17 today, which is kind of the last of the equilibrium chapters. 15, 16, and 17 are all together, which is why they're all in the same exam, right? As much as we could put them all there. Right? So 15, 16, and 17 are kind of all about equilibrium and calculating K's and understanding and applying them and putting them into use in specific, right, in specific instances, right? So that's kind of the challenge that comes on this next exam there, is just remembering, you know, what does K for a specific instance tell you, and what, you know, what do we need to calculate it, and when do we use a KA versus just KEQ versus the KC versus the KP, and all these other kind of things that come along with it, right? Lots of Ks. So the challenge here is making sure that we're appropriately applying equilibrium expressions for the questions that come up, right? For the problems that come up. But anyway, chapter 16, we learned about acids and bases. Right? We learned about strong acids and strong bases and weak acids and weak bases, and what happens with the K's for those. And what we're going to be doing in chapter 17 is taking those ideas and then, I guess in general, just looking at two broad topics. The first one is this idea of titration, and titration is just basically doing acid-base chemistry. Right, but just seeing how do we want to verbalize this? Taking a neutralization reaction and figuring out the individual steps along the way. Right, what happens when it's halfway neutralized, so to speak? Or I believe you guys did a titration in lab, right? When you guys were doing like the bleach, you guys were looking at color changes and this kind of thing. So it's going to be that same idea, except with adding some of the intermediate steps in there, right? But it's handled the same way, right? It comes down to K's and paying attention to what the information is that we have. That's going to be a tricky part that comes out of this. The second part of chapter 17 is going to be going back to this idea of solubility. Right? Remember, in the first semester of general chemistry, we talked broadly about the solubility rules, and we've made these blanket statements like, if something has a group 1A metal, then it is soluble. And okay, all right, group 1A soluble, right? You know, and then we said, well, if it has calcium, sometimes it's slightly soluble. Oh, okay, yeah, slightly soluble makes sense. But now we're actually going to come back and put numbers with that. Because solubility is basically equilibrium, right? Whether it's in solution or not in solution, right? Whether it's dissolved or not. And so we're going to talk a little bit about how we can apply equilibrium to calculate exactly how much stuff is in solution, or how much stuff can be dissolved and go into solution. So those are the kind of two broad topics that come out of this chapter here, okay? So honestly, the slides and all this stuff, there's not that much. And so we're going to be spending quite a bit of time just kind of working through some practice problems. Like we typically do, right, once we kind of finish up all the notes and the in-slide examples and these kind of things, right? So again, I think I've said it for the millionth time here, right? There's no big secret to how to be successful in Gen Chem 2, right? The big secret is showing up to class, which you guys did, that's good, right? And the second secret is making sure you guys are spending time outside of class. Make sure you guys understand these tricky things like equilibrium, right? The point that I'll make again is a point that I think you guys already know, right? I see you guys for 3 hours each week, right? And we've gone through, let's see, 1, 2, 3, 4, 5, 6, right? We're about to finish our 7th chapter, right? But I see you guys for 3 hours a week, right? Make sure that you guys are spending the appropriate time outside of class, right? Making sure you guys are reading through your notes, making sure you guys are reading through the book, or watching videos, and working problems, all these other things to make sure that you guys are successful with this. Right? We have an exam coming up, okay? We have an exam coming up next week, right? On all this stuff here. So hopefully you guys are preparing and doing and practicing and getting together any of the information that you guys need to be successful and to do better on this upcoming exam, right? All right, so I think that's kind of the overview with that. Yeah.
Is there any possibility you could provide practice exam preview to Laura so she knows how to help us prepare for this one?
Sure, it's called the back of the book. End of chapter problems. That's it. I mean, I'm not trying to be facetious or dismissive. I'm just saying that's what I look for. Right? That's where I do, that's where I go, and when I pill problems on quizzes and exams, that's what I look for in there. Right? So now your question is, well, which ones in there are important? Good question. Right? So the answer to that is, the approach that I say to that is, well, they're kind of broken down by section, by topic. Right? So open up the back of the book, right? Go to the different chunks of problems that are in the back and start working at the first one. Right? If you get the first one right, okay, skip down a couple, right? Work on the next one. If you get that one right, keep going through, right? If you make it through the whole section, then that's probably a good understanding of that concept, right? But if you get the first one wrong, then that's what you know you need to focus in on, right? I'm not saying you have to work every single problem at the back of the book, right? I mean, if that's what it takes, then do it, right? But I'm just saying, use your time wisely also. I understand you guys have other classes, right? But everyone in here has a different way of learning, a different method, right? And what I will say about Laura is she's been around me long enough to know I ask questions anyway, right? So she always knows that I like you guys to explain the ideas behind what we're doing the math also, right? So that would be the other thing to pay attention to while you're working through these problems. Because you guys understand what you're doing when you're setting up these problems, right? And as always, I'm always around for you guys if you get stuck in one of them, right? Just swing by the office. You guys are more than welcome to come ask questions, right? All right, in terms of other things, so there should be a quiz that opens up on Wednesday for you guys here. Just more acid-base stuff, those kind of calculations. Let's see, labs this week for you guys again, right? Yes, right? So I got another lab, make sure you guys are prepping for that. And I think that's kind of all we need to check with you guys about. Okay, cool. So we'll get started with some prayer, and then we'll start to look at some of these ideas that come out of chapter 17 there. So Lord, we just thank you for another opportunity. Lord, we just thank you for some time to relax, some time to refresh, and some time to get our feet back underneath us, Lord. Lord, we just pray for the energy that you've given us, Lord, just to be applied to something useful and productive, Lord. Just help us to use the resources that you give us to further your kingdom. Just help us to be good stewards of the things that you do provide us with, Lord, our time and our money and our efforts and our intelligence and whatever it is, Lord, that you've gifted us, Lord. Just help us to be appreciative of those gifts and help us not to squander them, Lord. We just pray this in your name. Amen. All right. So, let's take a look at, obviously chapter 17 is not called More Equilibrium, but we might as well call it 10. All right, so anyway, so I told you guys we're going to learn about titrations, and that's fine, but it's kind of within this context of things called buffers. Now, buffers are extremely important, especially when it comes to biological systems, right? Your body is essentially a giant buffered system that works with different types of buffers in different regions of your body, right? For those of you guys moving on biochem and probably molecular biology and these kind of things, you guys will learn all about that stuff there, right? So we'll talk about the different pH ranges and what happens when you go above or below that, and these kind of things and what influence that has, right? So what our purpose is here is just kind of introduce the mathematics behind this. How can we calculate buffer strength, and how can we, let's say, figure out how much the buffer capacity is, right? Those kind of, let's say, quantitative values that come out of these ideas, right? That's kind of the general idea of all of Gen Chem 2 is, now that you guys understand the idea, let's put math behind it and figure out what the numbers are that comes from it, right? So that's kind of the idea here. All right, so how do we make a buffer, or what's the definition of a buffer? You know, I think the book kind of rambles through some, you know, paragraph definitions, and just for laughs, I kind of looked at well, not really laughs, I don't mean that in a derogatory way, but I looked through the Wikipedia entry for this, and it's pages and pages of description, all this kind of stuff. And they're all right? You know, that's all correct, but let's try and boil that down a bit. Buffers need a weak acid to react with any added base, and they need a weak base to react with any added acid, right? So basically all we're doing, well, I have to be careful when I use the word basically here, right? So in essence what we're doing, right, we just have weak acids and weak bases in solution, and they're going to react with whatever's added to it, okay? And the idea is they have to be weak acids and bases. Why? Well, remember, weak acids and weak bases are going to behave like weak acids and weak bases. They're going to establish equilibrium, okay? At the end of the day, the way I kind of think about buffers, and you know, it'll maybe become evident as we work through some of the math, right? When we have a buffer, we are stressing the system by adding something to it, okay? So imagine we have a buffer that has a weak base, and we add some acid to it. What are we doing? Well, we're basically just going to play around with the equilibrium, and it's going to reestablish itself, right? Based off of the reaction that happened. So it's kind of a combination of our equilibrium and our Le Chatelier's principle ideas. That's kind of how I think about it here, right? We're adding something into this which shifts and reestablishes our equilibrium at a different position, right? It's going to change some things. There is a reaction that's happening, right? That's the distinction here, right? We are going to, like it says on the bullet points, if we have a weak acid, we're going to add base to it, and an acid-base reaction is going to happen, right? Which is going to disturb the equilibrium to an extent, but it's going to reestablish itself, okay? So that's kind of the idea, right? A buffer's purpose in life is to prevent drastic changes in pH, okay? And that's kind of what we'll show here graphically and mathematically as we get through this, right? And I think some of the examples that we worked last chapter, you know, even if you add a small amount of a strong acid, we can shift our pHs by several orders of magnitude, right? But if we add that strong acid to a buffer, then it's not going to have that big of an influence on it. That's the whole idea behind them, right? Big shifts in pH in biological systems, well, that's, you know, that's a recipe for bad times happening, right? The third point there is that the weak acid and the weak base shouldn't react with each other. Usually the most common buffers are conjugate acid-base pairs, okay? Conjugate acid-base pairs. Obviously, if you have a weak acid and a weak base and they're reacting with each other, then, right, we don't really have a buffered system there, right? We have something else that's going on. So we need a weak acid, we need a weak base, and they don't want to react with each other, right? Typically, right, this is what we end up looking at here, right? Something like a conjugate acid-base pair. Probably the best example, the one that we see most commonly is, this is acetic acid, and this is its conjugate base, sodium acetate, right? Okay, now there's quite a few different types of buffers that can be made. I venture to say, if you guys go to Google and just type in, how do I make a buffer from, you know, whatever, right, acetic acid, it'll come up with pages that automatically have all the calculations there and all these kind of things. I know you guys are shocked to know that there's you know, amazing information out on the internet, right? Right? Aside from adorable dog videos, right? There's also information about buffers and how to set these things up, right? So for any of you guys who are working through and doing some biology research, I'm sure you guys will come across that stuff already, right? But especially when you guys are going through some of these upper division courses, you guys will spend a lot of time kind of dealing with buffers here, okay? All right, so there's the definition, if we want to boil everything down, a chemical system that resists large change in pH, okay? So a couple of things here, right? We are going to see changes in pH, okay? If you have a buffer and you add an acid to it, it's going to change the pH a bit, right? Because we're going to be doing an acid-base reaction and reestablishing a new equilibrium with new concentrations, all this kind of stuff. So we are going to see a change in pH. It's just not going to be as much as we anticipate or expect it to be if we were adding that acid to a neutral or just aqueous system, so to speak, okay? That's the idea here. All right, so just to kind of put some numbers with all this, right? If I have some pure water, right, we assume that our pH is 7, right? If I add just 0.01 moles of either that acid or base, right, we have a massive shift in our pH one direction or the other, right? Now, hopefully at this point you guys could calculate that concentration given the values that we have here, right? We recognize it's a strong acid, so it completely dissociates, wanders through all that kind of stuff, yada, 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 right? But if we have a buffered solution here of acetic acid and sodium acetate, we're going to figure out how to calculate the initial pH, right? And after we add the exact same amount, we really don't see too much of a shift in our pH for the overall system. That's the whole point, okay? That's the whole idea here. I know you guys are itching to know how to get those numbers. Don't worry, we'll get there in just a second, right? But this is the whole idea about why we develop buffers and all these kind of things, right? Cool. All right. Okay, so let's put some equations with this, and pretty much the only equation that we'll use for this first part here. So what is the pH of buffered solutions? Well, it's going to depend on the acid-base concentration. I know that's a shocking statement there. Wow, pH is dependent on the acid-base concentration. Amazing. Okay, so the Henderson-Hasselbalch equation there is what we're going to be using. So if you type that into YouTube, or I believe I already have the videos posted for you guys for this kind of stuff here. But if you guys want more information, I'll just type that in. So you notice there at the top, I just took the expression for Ka and I rearranged it to solve for the hydronium concentration, right? And then if I take the log of everything, right? If I take the log of this equation there, right? That's the expression that we get out of it. And then if I take the negative of everything, right? So if I take the negative log of hydronium, remember that's our pH. If I take the negative log of Ka, that's our pKa. And if I take the negative log of this, right? Remember, if you take the negative of a log, all you do is swap the values that are in the fraction, right? So this is probably the most common expression for the Henderson-Hasselbalch that you'll see. pH of the buffered solution is equal to the pKa plus the log of the base concentration over the acid concentration, okay? The most important thing you guys can do when you see a new formula is just figure out what in the world does it actually tell you, okay? The Henderson-Hasselbalch is our way, primarily, I guess, of calculating the pH for a buffered system, okay? It is also a way of us relating the pH and the pKa of a buffered system. Got it? Why is that important? Well, can you guys measure pH in the lab? Sure, right? We got the pH meter, we could do that. And if I know the pH, then I can back out some of these other values for it, okay? What's a Ka? Well, Ka is just our equilibrium expression for the acid, right? The acid dissociation equilibrium. Can you guys look up Ka values? Sure, right? There's that giant table that's in the back of the book, right? I forget the exact table, but I mentioned it in one of the quiz questions for you guys, right? Or was it Appendix B or something like that, I believe, right? And then, if we know the concentration of the acids in the base, then that's all there is to this equation. pH, pKa, concentration of acids and bases. 4 things that you guys need to know. Got it? So if I ask you a question about this, what do I need to give you information about? 3 of those. Right? Otherwise you guys can't solve it. Guys with me on this? Right? That's all it is. It's so important to recognize. Note that the pH is going to be equal to the pKa when the acid-base concentrations are the same. Okay? Because the log of 1, right, is going to be 0, right? So then pH is equal to pKa there. Okay? All right. Common buffers that I define as common for no reason besides I think they're in the book. So, right? Anyway, when you're looking at a table of buffers, you kind of have to pick, what pH you want it to be buffered at, right? Certain proteins and enzymes and biological systems need to be buffered at specific pHs, and there's just a listing of these. Now, if you take a look at all of them, right, starting up at the top there, lactic acid is the weak acid, its conjugate base is the lactate ion, right? There's its Ka, there's the pKa, and all these kind of things that go along with it, right? So all of these, I believe, yep, all of these are just conjugate acid-base pairs, right? The quintessential way that we have of developing a buffer, okay? All right, so do you need to memorize all this? No, of course not, right? But just something for you guys to kind of take a peek at, and there it is. All right, so I've already talked for a whole 15 minutes. So let's start off with something a little bit easier here. What's the pH? And I give you a bunch of blah, blah, blah there, right? So first use of the Henderson-Hasselbalch, right?
What's the P?
Hmm?
What is P?
It's a mathematical expression, right? It's a negative log of whatever it's working on, right? So P of H means a negative log of the hydrogen concentration, right?
No, but I mean the P here, for the Ka.
Negative log of the Ka, right? P, this is just negative log, right? That's what I'm saying. Just a function, right? You could take the negative log of whatever, right? Then you just put that lowercase p in front of it. Okie dokie. So let's see here. So our pH is our question mark, right? So what is the pH? So we need information about the pKa, right? We've got the Ka is equal to 3.2 times 10 to the minus 3. Okay. Let's see what other colors we got here. Green. Right, we've got A minus, and we've got HA, right? So remember, A minus is our base. Okay, so one thing to start to pay attention to is how do we identify what our base is? I'll give you a hint. It's the one that doesn't have the word acid next to it usually, right? So, I know, there's these subtle clues that I work in there for you guys, right? But let's say that I don't give you the name pyruvic acid. How do you guys start to identify what a base is, right? Now we got to really think about this for just a minute. This is important. This is probably one of the more important lessons, right? So a base. Let's ask the question this way. So what is a base's purpose in life? Its basic function, if you want to. Right.
To accept a positively charged
Okay.
hydrogen.
To accept a proton, something that's positively charged. So if I'm a base, what usual charge am I going to have?
Negative.
A negative, got it? Okay, something to think about is start to look at the pattern of these bases. Where does that negative charge usually end up on? Right, what atom, these kind of things. Now, another thing that I told you guys about was the adikitis, right? Yes? So what's the name here? We have something called pyruvic, right? And its conjugate is pyruv 8. right? So taking a look at the names, right? Your 8s are typically your negatively charged polyatomic ions, right? Now, we don't classify pyruvate 8 as a polyatomic, right? But the same idea here is all I'm trying to get you, right? Nitrate, sulf 8, carbon 8, right? Your 8s and your ites are typically your negatively charged ions, is all it is. Got it? Right? So if you're looking and you don't exactly know what your base and your acid is, take a look at the name, take a look at the charges, right? There's another clue here. I tell you that it's sodium pyruvate 8, right? What charge does sodium have? Positive, so whatever it's bound to has to be negative. Got it? You see, there's a lot of clues in here. We just have to think about it and work it backwards, right? And think about what it means to be a good acid versus a good base. Okay, bases typically are going to have negative charges. That's a good place to start to look at it. What's that?
So the base is on top and the acid is on the bottom?
That's it. Yep. Well, the concentration of, right? Concentration of. Okay. Let's see. Green then is what we said for that. Right, so our A minus concentration is our base, right, that's this, so 0.06, and HA 0.05, right? Good? Let's see, we have an equation with 1, 2, 3, 4 parts to it. How much information are you given? 3, right? What's the only thing we have to do first? We're given information about Ka, but we need the pKa. Got it? So don't forget, we're given information about Ka, so take your negative log of that when you guys set this all up. So pH, whoops, did that in red. Again, pH is equal to negative log of 3.2 times 10 to the minus 3. Plus, I need to keep reminding myself about this. Plus the log of 0.06 over 0.05. Cool. So if we break this down, I got equal to, this was 2.49. This was basically plus. I forgot everything over the break. All right. Okay. So the negative log of that is 2.49. If we take the log of these two things here, 0.08. So we add those two together, right? So we get 2.57, right?
Mm-hmm.
Yeah. Cool. So 2.57. Good. That's not too bad, right? What does that tell us? Tells us the pH, which tells us what?
How much? I don't know, I'm too tired to function.
It tells you you're too tired to function. That's something important to know, right? There's this thing called coffee. It's great. Drink a lot of it really, really, really fast. It's the old jittery. What does the pH tell us?
Concentration of hydronium ion.
Right? That's the negative log of the hydronium ion concentration. So could I ask you a question like, what's the concentration of hydronium in this buffer? Yeah, you could do that, right? Yep.
How do you undo a negative log?
10, right? Or 10 to whatever is getting rid of your negative log. Right?
Okay.
It's log base 10, right?
Yeah.
Is what it is. Take a look in the slides from the previous chapter. I think there's quite a few examples that we worked through it in there, right? Cool. All right. So pH, the only point in me asking that is remember pH is pH. Okay? It doesn't matter kind of how we get there. If I know what the pH is, I can figure out what the hydronium ion concentration is. You guys with me on that? Right? Because this isn't the only way we have of calculating pH. That's all I'm trying to say, right? This is the way of calculating pH for a buffer, but it's still just a pH. Okie dokie. different here, right? What's this question asking?
I don't know.
So it's asking what is the ratio of what, right? So HPO4 2 minus and H2PO4 minus. Okay, so what in the world are HPO4 2 minus and H2PO4 minus? What is their relationship to each other?
The HPO4 2 neg is the base, and the other one is its acid conjugate.
Got it? They're just conjugate acid-base pairs, right? So what do we mean by the ratio? Well, ratio is just you divide one thing by the other. So what is this thing asking here? Well, they give us a pH, they give us a Ka, right? And so the only other thing we need to do is figure out the base over the acid, right? That's our ratio. Got it? Do we have information about pH? Sure. Do we have information about Ka? Sure. So can I figure out the value of this stuff in here? Sure. Right? I mean, I would do this a little bit differently. Yeah. I'll show you here. I'll show you the way I'll set this up. It looks okay, but I think you brought in an extra, I think you brought a negative in there that shouldn't have been. So, let's see here, 7.4 equals a negative log of 6.2 times 10 to the minus 8, right? Plus the log of, I'll say base over acid, right? Okay. So let's see here. Oh, I didn't write that down. Somebody give me this value right here. Should be something like close to negative
7.2076.
7.2076?
Yeah, I just used 7.21.
7.2076, okay. So we got 7.4 equals 7.2076 plus the log of base over acid, right? So subtract 7.2 from there. So what do you get? What is it, about 1.9?
0.19.
0.1, yeah. 0.192 equals the log of the ratio there that we want, yes? So if I take 10 to this, that gets rid of this, right? So if I take 10 to everything in here, so 10 to that, 10 to this, and that's going to be equal to, just going to write it out, 10 to the 0.192 is then going to be equal to the ratio that we want. Got it? So what's that equal to there? 1.5 something? 0.6?
No, I got negative sign for no reason, it's 1.5.
Yeah, let's say I got 1.5 something. Good? It's just asking for the ratio, it didn't ask what necessarily B to A is, right? Or what base in the acid is. So I'd have to give you other information about that, right? Good? What's the other thing to recognize about this? Well, if I give you information about B or A, we could figure out that concentration using this approach to solving the equation. Got it? That's the other method to understand here, right? If I give you more information, then we can back out the concentration of the acid or the base if we have that ratio, if we solve it this way, if we're given information about the pH and the pKa. Got it? So it's just a practice, let's say, of using our equations and rearranging them. Not too bad so far, right? Yeah.
So if you're undoing a negative log by raising 10 to the negative log or something, you
Yeah.
have to then carry that sign over to your answer?
Yeah, you need your negative, right? So if this was a minus here, right, then, or if we have to get rid of a negative log, right, then we'd have that minus sign to take care of also. Okay. All right. So now that we know everything there is to know about the Henderson-Hasselbalch equation and the 10 minutes that we've talked about it now, right? So let's talk a little bit about how they actually behave like buffers. All right. So if we add an acid or a base to a buffer, what happens? Well, I think you guys will be shocked to know that if you add a base to an acid, the acid and the base are going to react. Okay? And then if you add an acid to a base, then the acid and the base are going to react. That's all I'm telling you guys here. You guys with me? If you add a base, it's going to react with the acid. If you add an acid, it's going to react with the base that's present. Remember, a buffer is a ratio of your conjugate acid-base pair. There's some acid, there's some base. So just pick the one that's going to react with whatever you're adding into it. Got it? Okay, that's the thing to pay attention to there, right? Because the concentration of that acid and base that's in solution is what we're going to have to set up our ice tables with and our run through our math with, okay? All right. So if we want to just visualize this real quick, right? When we add an acid, it's added to the buffer, the amount of the conjugate acid increases, and that of the conjugate base decreases, okay? One thing increases, one thing decreases. Remember, this is the point that I was showing you guys on the previous slide there. Let me back up here for just a second, right, to draw your attention to this again, okay? So, right here, right, if I'm adding acid to base, I end up making acid over here, a weak acid. Now, what do we know about this weak acid? Well, it partially dissociates, right? So we're going to have to pay attention, right? We're going to have to pay attention to what we're adding and what gets made. Okay, the same thing over here. I guess I put right up at the top there, right? If I have the acid and the base, I make a conjugate base of a weak acid. And that conjugate base can go on to react with water to make a little bit more hydroxide, okay? So we're reestablishing an equilibrium. That's kind of the point that I was saying there at the beginning of this, of these slides, okay? We're dealing with weak acids and weak bases. They partially dissociate. A conjugate base of a weak acid can go ahead and react with water, right? We talked about that in the previous chapter also there, right? We were talking about what happens when you neutralize weak acids with strong bases. That is very important stuff that's at the end of chapter 16 there, right? Or, yeah, chapter 16 is what it was, right? Good, you guys with me on that? So that's all I'm trying to show you guys here, right? That the relative concentration of those change, okay? So that's what the graphs are there telling you guys about. That's why it's important to recognize if you're adding an acid, it's going to react with the base. If you're adding a base, it's going to react with the acid, and which concentration changes. Now there's something else that's important. Okay? You guys know that it's important, right? But I'm just going to draw your attention to it again. Okay? When I ask you guys for an equilibrium expression, okay, K is equal to what? Concentration of products over concentration of reactants. You guys with me? What unit is it in? Concentration. Now, when you're doing a titration, when you're making a buffer do its thing, right? You have a beaker, okay? That has your buffer in there, okay? It has some defined volume. How do we know that it has a defined volume? Well, remember, right? It's based off of the concentration of the weak acid, weak base. Got it? Then I add acid to it. What changes? Well, the pH is going to change, but what else changes? The volume changes. okay? This is the important thing to pay attention to when you're walking through these reactions, okay? You have to pay attention to the volume of stuff that's added. Most of the time when I work through these problems, I take everything into moles and work it all in moles and then go back and turn it into concentration at the end, right? Why? Well, moles aren't affected by volume, right? Moles are moles. You guys with me on this one? Right, if you leave it in units of concentration, you typically have to, okay, what's my total volume? You can do it, that's fine. I'm not saying that's a wrong way of doing it. Just you have to be careful about dealing with concentration in these types of problems. That's where the majority of the mistakes are made. Okay? Think about the total volume, because remember, concentration is an expression of volume of solution. If I mix two things together, my volume increases. And so I have to recalculate, I have to reassess my concentration at the end of that. All right. So let's see what happens here. 1 liter buffer is prepared with yada yada and some blah blah. Right? Calculate the pH of the buffer. Okay. And then after 0.1 moles of sodium hydroxide is added. Okay. So A is just more of what we were doing beforehand. So see if you guys can get A worked out.
Did we ignore the sodium?
Sure, go for it. Mm-hmm. Well, what does that tell you, right? So that's 1 liter of solution that you have, right? So take a look. This is what I was trying to tell you guys there. Always pay attention to not necessarily just the concentration, but the units of everything. That's part of your equation, right? So here, right, this is concentration of the base in the acid, right? And then in the next problem, I'm telling you, you add, right, you're adding 1 mole of that. So how's that going to change the values of the stuff that you have that you're dealing with? That's why I have to give you that information there, right?
Oh, okay.
So that's what I'm saying, right? Paying attention to units is really what it comes down to. Okay. That's good. If you guys got part A, see if you guys can start working on part B there. Thinking about what happens, right? We're adding sodium hydroxide, a base, right? So what's it going to be reacting with? Good? Are you with me on this? No, we're gonna have to do a little bit more shenanigans with that. Hang on. Right? And if we plug that all together, what do you guys get? For part A there.
7.006.
7.006, something like that, so 7 essentially. Cool. Good? Nothing too unusual there, right? So now we gotta think about what the second part is asking us then, right? So let's take a look here, right? So after that is added, so we're adding sodium hydroxide. We're adding base, okay? So it's gonna react with the acid part of this. So what we need to do is set up a table that can tell us about how things are coming together, right? So first things first, let's see what is happening here, right? So our acid, the H2PO4, 1 minus, right? The acid from the problem there is going to be reacting with the hydroxide that we add, okay? And it's going to make HPO4 2 minus, okay, plus H2O. Good? Everybody with me on this? The acid is reacting with the base that gets added to make the conjugate base and some water. Okay, that's a standard neutralization reaction here. You could go through and you could set this up with the HA and all that kind of stuff that we're used to, but I would advise against that, right? Just because it's very easy to kind of confuse what the different components are, and we need to know exactly the concentrations and stuff that we're adding into this. Good? So I always write out exactly the equation that I'm doing there unless there's some good reason for me not to, okay? All right. So it's kind of I'm being careful. I call these ice tables, but they're not necessarily exactly the same ice tables that we're talking about in the previous. Now, I don't mean they're completely different. What I'm talking about is we're not necessarily recalculating equilibrium. Got it? What we're calculating here is, hey, we're doing a reaction, okay? We're doing a reaction with the acid and the base, and let's see what the values are at the end of it. You guys see that subtle difference in there? Right? The change is not dealing with necessarily shifting our equilibrium, it's just what happens as the reaction goes on. Okay? I'll show you guys here with numbers, and that'll probably make more sense. But the beginning is no different, right? The beginning is no different. So what is our concentration of this? Well, it's 0.4, okay? Now be careful. I should have said this before I started putting numbers down. Be careful. Because I'm saying that we're adding 0.1 moles of sodium hydroxide to this, okay? So what does everything have to be in units of?
Moles.
Moles or concentration, one or the other, got it? But I told you guys at the beginning of this that we're dealing with a 1 liter solution. You guys with me on this? So that's to make our math easier. If I have a 1 liter solution and it's was it 0.4 or 0.04? 0.4, okay, right? So if I'm 1 liter solution and it's 0.4, how many moles do I have? 0.4. You guys with me? So in this case, it's not going to matter, okay? But always pay attention to that, okay? Pay attention to the units of the stuff that's added, the concentrations, all these kind of things. All right, so I start off with 0.4 moles of my acid, and I have 0.25 moles of my base. Got it? Where am I getting that 0.25 from? We're in a buffer solution. I have some of my acid and I have some of my base. You guys with me on this? Then what happens? We disturb their happy life, okay, by adding 0.1 moles of the base into this. Good. You guys see where this is going at this point, right? So what happens along the way Well, over here, it's going to be 0.4, right? Minus that 0.1. The acid and the base are going to react with each other. Good? What happens to our hydroxide? Does all of it end up reacting? Do we have enough acid to react with all of our base is what I'm asking. The answer is yes, right? So how much of our hydroxide is left over at the end? No, got it. So this is 0, right? Okay. What happens on the other side here? 0.25 plus 0.1. Good? Because if we react our acid, it turns into its conjugate base. Okay? And do we care about water? Nope. Right? Remember, we're in the aqueous solution. Water's for all practical purposes, the water concentration is not going to change. All right. So here is our acid, right? Here is our base. Okay. So now let's get this set up, right? It asked us for our pH, right? So pH, does the Ka change?
No.
All right, Ka is a constant, right? At a constant temperature, it's not going to do anything. So what was it, 6.2 minus 8, right? Plus the log of our base, right, which is 0.35 over acid, which is 0.3. Good. So what did you guys get for that?
7.28.
7.28? Seems about right. Okay. So there are our two pH values for this type of problem, right? Or for this problem. Do my answers make sense? Well, what did I do? Okay, the first one I thought that I just calculated pH. Okay, I'll assume that we did the math right there. What did I do to this buffer? I added a base. So what should happen to my pH? It should go up, right? Well, did it? Yeah. Did it go up a lot? No, right? Did we add a lot of base to this though? Actually, yeah, right? 0.1 moles is quite a bit of hydroxide, right? Yeah.
How do you know that the OH is going to be used completely? Like with their
Yeah, so this is the stoichiometry, right? 1 to 1 to 1 to 1. Right? For every one of these, I'm going to react one of those. So for every 0.1 of these, I'm going to react 0.1 of those. Right? So you have to pay attention to the stoichiometry is what it is. There's going to be cases where you have hydroxide left over, and we'll talk about that, right? So you have to pay attention and just do the, I guess, mental math. Just, you know, do I have enough of this to react with the other one, right? What's up?
I thought the tendency for a base or an acid to react with one another was whether or not it was strong or weak acid or base.
It's true. This is a strong base with a weak acid. It's going to react, right? It's going to react.
Okay.
Yep. Yep.
Can you explain again why you use moles instead of molarity?
Yeah, so for this problem I use moles, and for most of them I use moles so that I avoid the issue of concentration. You'll see for one of the next problems that we work through, I change it to everything in concentration. And what I say is we have an initial volume of our buffer, and I add some volume of the base or the acid, right?
Okay.
And then here in moles, I can just do I can just directly compare those, right? But if I'm dealing with concentration, I have to be careful because the concentration is going to change as I add things together,
Okay.
right?
Yeah.
So it'll become a little bit easier when I work through one of those, but that's why I'm showing you guys, hey, work it in moles, avoid that issue. Now, to that point, right, be careful, right? Be careful, because we still assume that the volume is 1 liter at the end here, right? That's why we didn't say at the end, okay, go back and change the concentration, right? But always pay attention to the total volume of stuff that you guys are dealing with, okay? It's very easy. You work through these kind of complex problems, you get to the end, you just plug it in. Don't forget about to recalculate total volume at the end, if we need to, okay? In a case like this, we don't need to, but the next problem we will, okay? Good?
So even though in the equation it's log of concentrations,
Mm-hmm.
we can still use.
Because this is a 1 liter solution, right? This problem specified it was 1 liter. And I didn't change the concentration by adding anything to it. So it's just kind of a special instance, right?
You didn't change concentration, you said?
The volume, excuse me, sorry.
How did you not change the volume?
Because I did magic and made it not change. In reality, the volume would change some by adding something to it, right?
Yeah.
But for this purpose, we'll just assume it doesn't, right? I'm not gonna like trick you guys with something like, haha, I changed by 0.1, they didn't real, right? I will give you information about the volumes that you're adding together,
Okay.
okay? What's up?
How come we could still use the same Ka? I know there's a constant, but
It's the acid dissociation constant, right? The Ka of this.
even though, like, here, right, we wrote another equation with something completely different, like
Not completely different.
OH.
What is acid and base here? This is the weak acid and its conjugate base. What does Ka
Oh,
represent,
okay.
right? Ka represents that
Okay.
dissociation constant, right? It's just we did something to it, right?
Yeah.
But Ka is only affected by temperature, right?
Okay.
All right, good. I will see you guys on Wednesday then.